While studying measuring energy changes, there's going to be a variety of calculations that you need to perform. They include calculating the heat energy change for a reaction based on experimental data, calculating the molar enthalpy change for a reaction based on experimental data, also predicting the amount of heat that will be produced during a reaction, knowing a specific molar enthalpy, and also predicting the change in temperature for a specific reaction. Now, a lot of these processes are based around a procedure called calorimetry, which is how we actually measure the amount of heat released or absorbed, and we simulate this in a very simplistic way in our lab. Okay, so basically during the reaction, heat is either going to be released or absorbed from the surroundings. So what we actually do, or how we are going to measure this in the lab, is we have our reaction occur in an aqueous solution. So we've got a specific volume of water, and when the reaction occurs, we use a thermometer to monitor the temperature change to see if it goes up or down and how far it goes up or down. And we rely on the specific heat capacity of water. The specific heat capacity of water is equal to 4.18 joules per gram per degree Celsius. So what that means is it requires 4.18 joules of energy to raise 1 gram of water by 1 degree Celsius. So by monitoring how many grams of water or knowing how many grams of water we've got, and monitoring how many degrees it changes by, we can calculate how much energy has actually been released or absorbed by the reaction. And it is being either absorbed from the water or released into the water, hence the temperature change. So the specific heat capacity here of water is always going to be a constant. And the mass that you use to calculate the heat energy released or absorbed is the mass of the water that you have got to absorb the heat energy released, or where the energy is being taken in from the reaction. And the temperature change is what is actually recorded or measured and recorded using the thermometer. So looking back at our expression here, the lowercase q is the heat energy released or absorbed. The mass is the mass of the water, not to be confused with the mass of the substance being used. Delta T is the recorded temperature change, and Cp is your specific heat capacity of water, which is a constant. As with all calculations, it's really important to take note of the units. So we know that our mass of water is going to have units of grams. Now, when you measure out the water for this, you might use, say, 100 millilitres. There's a relationship between the volume and the mass of water. So 100 millilitres is equivalent to 100 grams, or 1 mil of water is equivalent to 1 gram. So we've got grams. Our change in temperature is going to have units of degrees Celsius, and our specific heat capacity of water has units of joules per gram per degree Celsius. So we can see here that the grams get cancelled out, the degrees Celsius get cancelled out, and we get left in units of joules. So this is calculating the heat released or absorbed in joules. Now, something else that you may be required to do using this same process is calculating the molar enthalpy change for a reaction. what you should notice is that this top line here is the same as what we were just looking at for the amount of heat released. Because essentially the molar enthalpy of a reaction is the amount of heat released per mole. So we're still looking at the same energy change, but we're now considering the amount of substance that has been used. We've also got the 1000 on the bottom line here, and that's because the molar enthalpy has units of kilojoules per mole, but we would have noticed earlier that that top line had units of joule. So that 1000 there is a conversion factor, so it converts joules to kilojoules, and that's because there are 1000 joules per kilojoule. So essentially they are the units that would be on that figure of 1000. So if we have a look at the units on this whole expression, the mass of our water is in grams, our temperature change is in degrees Celsius, the specific heat capacity of water is in joules per gram per degree Celsius. On the bottom line here, our 1000 has the that conversion factor has the units of joules per kilojoule, and the number of moles of substance has the units of mole. So if we go through again, we can see that the grams are cancelled out, the degrees Celsius are cancelled out, the joules are cancelled out, and that's what leaves us with our units of kilojoules per mole. Now, sometimes people can get confused about what the difference is between these two calculations and how they are different. So we'll just have a look at a quick example and have a look at how they are different, but also how they're related. Okay, if we have a look at the example of dissolving 2.5 grams of ammonium chloride in 100 grams of water and recording a temperature drop of 1.7 degrees Celsius. So the first thing that we can do with this information is calculate how much heat energy has actually been released or absorbed. And because we can see that we have got a temperature drop, that means that energy has been absorbed. Okay. So to calculate how much heat energy has been released or absorbed, we want to use the first expression there. So the heat energy released or absorbed is the mass of the water times the temperature change of the water times by the specific heat capacity of water. So having a look at the information that we have got in the question here. So if we're looking for our mass of our water, well, we have 100 grams of water. Our temperature change is our 1.7 degrees Celsius, and we know the specific heat capacity of water is a constant. So the heat energy absorbed in this case is our 100 grams times 1.7 degrees Celsius times 4.18 joules per gram per degree Celsius, which gives us 710.6 joules, which is approximately 710 joules to 2 sig figs. Now, because that's been absorbed, that is a positive value there. It means that 710 joules of energy have gone into that reaction, which is why we're seeing the temperature drop. Now, based on this information we've got here, we can also calculate the molar enthalpy of solution for the ammonium chloride. And to do that, we need to use the bottom expression. However, what we've already noted over here is that top line of the delta H expression is actually Q. So we can just write this shorter as delta H is equal to Q divided by 1,000 times the number of moles. So the first thing that we actually have to do is calculate our number of moles of ammonium chloride, which is equal to our 2.5 grams divided by the molar mass of ammonium chloride, which is about 53.5 grams per mole. Okay, so now we know how many mole we have actually used. So to calculate the molar enthalpy, it's the heat energy released. So that was our 710.6 joules divided by 1,000 joules per kilojoule times by 0.0467 mole. Now, in that calculation, we'll see that the joules cancel out, which is going to leave us with our kilojoules per mole on the bottom there. And we get approximately 15 kilojoules per mole. And again, because it's been absorbed, that means heat has gone into the system. It's positive. Now, if we know the molar enthalpy of the reaction for a given reactant, we can actually calculate how much heat energy will be released by using a certain amount. For example, how much heat will be absorbed when 7 grams of ammonium chloride is dissolved in 100 grams of water? We've just previously calculated that delta H for that situation is equal to 15 kilojoules per mole. So what we can do is firstly have a look at how many moles of the substance we have. So the number of moles is the mass over the molar mass. So that's our 7.00 grams divided by our 53.5 grams, which gives us 0.130 mole. So we can calculate how much heat energy is going to be absorbed by timesing the number of moles by the molar enthalpy. By doing that, we can see that 1.99 kilojoules of heat energy will be absorbed when we dissolve 7 grams of ammonium chloride in 100 grams of water. We can go a little bit further than that and go, well, if that amount of energy is being absorbed, what temperature change can we expect to observe? Now, to calculate that, we need to look back at our original expression, which included the heat energy released or absorbed and the temperature change. So that was that the heat energy released or absorbed is equal to the mass of water times by the change in temperature of the water times by the specific heat capacity of water. And in this case, we now know how much energy is going to be absorbed. We know our mass of water, the specific heat capacity, and we're trying to calculate the temperature change. So we're going to make that the subject of the expression. So the temperature change is equal to the heat energy released or absorbed divided by the mass times the specific heat capacity. Now, it's very important here that you take note of the units. So mass is in grams, temperature change is in degrees Celsius, and the specific heat capacity of water is in joules per gram per degree Celsius. What that means is that our heat energy change needs to be in joules. So carrying through our value from the first step, where we've calculated how much energy is absorbed, we need to convert that to joules. And it's that value in joules that we can then substitute into our expression. So we can expect to see a temperature change of about 4.76 degrees Celsius. So if we look back at the data we had at the start, we dissolved 2.5 grams of the ammonium chloride and see a temperature drop of 1.7. Based on this, if we dissolved 7 grams, we would expect to see a temperature drop of 4.76 degrees.